So good morning, everyone. Please let me know in the chat that you can hear me well and see me well, plus that this is okay. We will start shortly. So can you see and hear okay? Well, not in general, but can you see and hear the stream, right? So please respond on that in the chat. And also you already can get the template 4.2, and we're gonna jump in straight into the research paper. But first let's check that you are alive. Quiet a bit. Okay, thank you. So now is it better? So if it's still too quiet, let me know. I made it a little bit louder. Maybe I should. Now should be even more louder, hopefully. Really hope that this is now okay. So yeah, please get also template 4.2. This is going to be quite exciting, really interesting stuff happening today. This will be the Proxy NCA, the ranking loss. So let's go over the paper a little bit as well. First of all, the NCA, so near component analysis, quite old technique. So let me see, this is 2004 paper for Proxy NCA. So this is one interesting way how to also reduce dimensionality as well. So that's like PCA or principal component analysis or TSNA. So all of these could be used for the dimension reduction, and here in this case this will be really interesting application. So in my studies of the deep metric learning, this paper I think is one of the most interesting ones. There are some others also who are good, but this is really also really interesting. So first of all, we can see that they claim basically that the the accuracy for the top one pair is you can get much higher in the CARS 196 dataset, which is very popular for deep metric learning. And so the accuracy can be achieved much faster and much higher. Of course, if you would study some other papers for the lifted structure, triplet loss, and so on, they would not actually, they would say that they have much higher accuracy, but they usually refer to top 5, I think. That's why top 1 is not so high, but top 1 is actually much more meaningful in many sense. So you see that all others are not as good as they claim. So we will see that as well, that actually this method converges quite good. So then the way how it works from the paper, it's a little bit sometimes tricky to get it immediately, but we'll try to do this step by step. So first of all, they use proxies. So that's why it's called Proxy NCA ranking loss, but it could be used actually with triplet loss as well. So you could use some kind of other loss function as well, but the main idea here is about proxies. So if you have the just simple triplet loss, then in this case actually it's really a little bit funny that they draw this without actually triplets, because so the positive pairs are actually not here. So if it would be just triplet, there would be 1, 2, 3, but actually this is like n tuple loss. So all positive pairs are pulling together, all negative pairs are pushed away. But instead in this case, there are these two big things here, and these two big things are actually not the data points. So okay, we'll try to really explain step by step, and then we will implement, and then you hopefully will understand. So all of the small red dots are z vectors for positive, for basically for the same class, right? Maybe we should write it in a different manner, because positive and negative might not be. Okay, but let's keep it positive, because in the second picture the small point is the anchor. So the anchor is this one, ZA, that is our anchor. So these all guys here are Z positives, right? So you pass to the encoder the image, the picture of the car or some person, depending on the domain, and then you get those Z vectors, which you compare with the Z anchor, which is just one selected from the same class, right? So these are Z positives. And then there are Z negatives, right? So these will be all of the negative ones, right? So hopefully so far clear, because that was what we already did before with the contrastive loss, with triplet loss, harmonic triplet loss. So then here, ZA is here, and the other ZPs, you see they are grayed out. So we are actually not using them. Instead, we are using something which is called Proxy. So here, this will be not really Z anymore, but P, or maybe I should write some Proxy, I don't know. So Proxy P and Proxy N. And what then the Proxy P and what Proxy N is actually? So the Proxy P and Proxy N, then in this case, are learnable dictionaries, like embeddings. You could think of that. Maybe we should actually implement it as embeddings, let me think. It actually doesn't matter that much, actually. I'm not sure, really. It could be implemented as embeddings. I just realized that in my implementations before, I was just using matrices. But the matrices and embeddings are basically the same thing, just thinking if there is any advantage of doing that. But basically, those are just dictionaries, learnable matrices, learnable dictionaries which are represented as matrices. So again, let me explain. Where are the squares? So let's imagine this will be the proxy dictionary. So let's call these as proxies. Proxy dictionary. Dictionary or matrix or lookup table. Let's call it lookup table. So if I just saying it as a matrix, maybe it's not clear enough. So here there would be, for each class we have the kind of so the row, right? So there will be for the red class, for the green class row, then for some other classes which are inside there, right? For the blue class and so on, right? So and then we select from the learnable matrix. So this is just learnable matrix or lookup table. We select one of those rows. So if we are now looking at the red class, we select this row and put it here. If we are looking at and we need some negative pair here, and the kind of the hardest negative pair is actually this green one, then we select that one here. No, we select for that one here. So basically, there is still the sampling process and selection process, because we need to know which the negative we should select. Is it the green one, the blue one, or maybe there is also the yellow one? Well, so just to make sure that you understand that there are all of the other classes also in that matrix. But we are not using them now because we selected that the pair, which is the most like the one which we should use for the negative one, was the green one here. So basically, again, just to explain. So the proxy table is just something we use in the loss function. So this is really interesting way of model and the loss function, because the loss function itself contains of learnable matrix or learnable lookup table, which is only used for the loss function, and then the final production model do not use this lookup table at all. So the lookup table, the proxies, are just for the training purposes, not for the inference. So this is really interesting that inside the loss function you have learnable parameter, which is something that I don't remember we had looked at something like that before. So is it clear so far? Is it clear so far? Plus, minus, if something is not clear, let me know what exactly is not clear. Because you already know the contrastive loss, the triplet loss, and now you see that there is additional complexity layer on top of it. So we select from different types of cars, right? We select a set of cars which are from the same class, so these will be red ones. Then we want them to pull them together by one arbitrary selected anchor, which is from the same class. We want to push away all of the other types of cars, right? And then, if we look from this new method from the proxies, then we want to use some kind of learnable lookup table where each row represents different car, and then we match the car which we were referring to. So we basically define that first row will mean that car, the second row will mean second car, and so on. And we use it as a proxy, so we want the model to learn this, like where the center of the mass for each of the clusters is located in the space, but at the same time we do not tell where exactly the center of the mass is located. This is really interesting approach. So, and this approach where we say that, I see that there are pluses, which is really good. So if we say that these are the class assignments, right? So this will be then the first class, it's like 0 class, first, second, third, 4, and so on. So this method is called in their paper static assignment. You will see that there are also another type of assignment which is definitely more interesting, but also much more harder. But basically here, this is something where we predefine that each row belongs to each class. So that is static assignment here. Just to maybe go one step back from here, I've just remembered one really interesting thing. These kind of models of deep metric learning, where you try to classify something in the embedding space, right? They are also not only better for kind of explaining semantic similarities in the embedding space, but if you have these kind of proxies, like the kind of ground truth locations of the centers of the mass, which in this case are not known, which will be learned, right? But if you would hypothetically, if you would know where they are located, right? Then you would actually be able to train them directly to target those, to reduce the distances to actual positions in the embedding space, right? And I know that there is something called circumplex models, which are really funny a little bit. So, okay, let me quickly copy. So that is from the other line of research what I have been doing. So This is for the emotions, but this could be done also for any other classification task. So this is again really interesting approach. So okay, so this is not deep metric learning exactly, but this could be another. So this is something between some. So this is called, first of all, this is called circumplex. If I remember, if I wrote it correctly. Oh, no, I did not wrote it correctly. Circumplex. Yes, and then this is this is in between classification and deep metric learning. What we are doing right now, what we are doing right now, also with proxy ranking loss, or it's sometimes also called proxy NCA ranking loss, or just proxy NCA loss, doesn't matter. So what we are right now doing in all of these course series are deep metric learning. And before, in the introduction course, we did classification, right? But I somehow forgot to mention that there is something in between. So the circumplex model is somewhere where the human labeler puts some points in this embedding space. So if you imagine this is an embedding space with different classes, and then we can simplify tasks. So the task would not be like in this case where we need to learn the centers of the mass where they are in the space, but some labeler already put those centers of the mass, and then the model would learn to put the Z embeddings as close as possible to those modalities which person has placed there. And you already can see that there are some really important behaviors, like properties for these models, which are much better than classification models. So if your labelers are like have enough time, it's much better to not just classify by classes, but put them in circumplex model, where you actually place in some kind of arbitrary Z space the similarity between those classes. Because what it means is that if I have just softmax, right, then in softmax we are training with the cross entropy, where it just means that any class is 0, 0 probability, 1 probability, right? Then 1, 0, 0. And there is no actually way in the whole like procedure of the loss function or the model to measure, like to have kind of similarity between those classes. I mean, like it doesn't matter the order, it doesn't matter if some class is more similar to other class, all of that is lost in classification. It's completely lost. So, but instead of circumplex model, where you have where you model the ground truth with Z, you already see that some classes are more close together, some are further away. So you see that the classification, I think in general, is simple method that works in a lot of cases. But as soon as your kind of class distribution is not as uniform as you would like it to be, then in that case you should use either the circumplex or deep metric learning. So is this clear so far? So is this clear so far? Plus, minus. By the way, again, this is just a step back. We are not going to do circumplex model today, but I just wanted to let you know that there are at least 3 ways to do the like a classification re-identification tasks, basically. With circumplex model, it's actually classification. So basically, you can do classification in one, so like cross entropy plus softmax, right? Old way, then the circumplex with the predefined Z ground truth, right? And then 3 is deep metric learning, which is DML, which are what we do right now. So this is contrastive, triplet, and now proxy NCA type of loss. The proxy NCA is the most similar to the circumplex, but the difference is that proxy NCA is that made in a way that we don't know actually the ground truth center of the mass. But again, I just wanted to show you this because in real life problems, I think not many problems are uniformly distributed in the class probability so that softmax would work always the best. So in most cases, circumplex would work better, but at the same time, there is additional complexity because the labelers are not then allowed just to label like one class by another class, which is much easier for human being, but they need to kind of put them in the similarity space, which is a lot harder for labelers. So there are some drawbacks also to the circumplex method. So okay, happy to introduce this part. So let me go next. So again, proxy NCAs, this is what we are focusing now today. Then the last missing piece, so actually maybe there are two missing pieces. One is the loss function. So the loss function is this thing. So this is also can be used not only for proxies, but for like in this case, distance between some data point and between the kind of the some data point, some other data point, and all other data points. So that would be a kind of definition for the NCA, because NCA normally should not be informed by the class itself. So that just try to maintain the distances in some. So if you reduce dimensionality, try to maintain the same distances in reduced dimensionality. So if you had like an embedding space of 32 dimensions, and then you reduce the embedding space to 2 dimensions, you want that the distances in 2 dimensions represent the same distances in the 3 dimensions. So that is basically what is the NCA. So this is really simple dimension reduction method. At the same time, I think really nicely written. So you could actually implement that even as like a model small, but it's not like something you learn and then use. It's just a method to like iteratively in a lower embedding space maintain the same distances as in higher embedding space. You would have a really nice picture, but it's not actually the purpose of the model. So here there is actually the model. Again, the loss function looks exactly the same, but the terms are changed, which is really important actually. So let me dissect the loss function a little bit. So here, by the way, I think that the static assignment method, which we will do first, but what I explained already, that we statically assign each row to each class, that method could work probably also without specific triplet sampling for the contrastive loss maybe. Also, this part of the proxy NCA loss function could be replaced with triplet loss or some other function, but at the same time, I think one of the reasons what they put in the paper, they say this works so well because we are using something that looks like softmax, basically. Of course, this looks something like softmax, but it's not softmax because there's distances there, right? So, and they say that we prove by this method that we use proxy NCA here and it gives better results, and there is a proxies in between, that the method which I explained already before, by adding to the contrastive loss or triplet loss the softmax at the end, so that initially the clusters would collapse faster, is just like one specific case of this method. So they say that they have more generic method that explains why the softmax addition to the triplet loss gives better results. I think that is one of the reasons why they chose this loss function instead of some other loss function, because they wanted to say that they can now explain why the softmax helps triplet loss. But anyways, a part of that, we can implement this. So there is a sampling of the triplet, which we already kind of have. Maybe the only thing which, maybe we should rewrite it a little bit. So but we have some anchor. We want to select from the anchor the good combination here for the positive pair. Again, the way how they wrote these equations really confusing for a person who is not very familiar with deep metric learning, because I would write this as an anchor, this is a positive sample, and these are all other samples. So instead, they just made it really confusing. So these two are then the positive ones. Then the P, what is P? The P is the embedding matrix, so that we're just selecting out from the embedding matrix one proxy there. So this is really simple stuff there. Again, the way how it's written here, not clear at all, because I would never write it like passing as the actual embedding to the some kind of model, but instead what it actually is something like P with the index of y and P with the index of z. So it's just selecting out the proxies from the matrix, not actually having some kind of function execution. And again, I think this is really good that we are looking at some real life papers, some really scientific papers which are highly rated. For example, this paper is made by Google Research, and like really, I think this is one of very good papers that they had. And you see that the notation, how they write things, is always different. So this like I have also in the math, it's like you can write the same thing in so many ways. So you think that like in some equations in the I don't know, linear algebra or calculus, you only can write things in one way. You know, like there's rules for that. Like when you're starting to write novel scientific papers, and then the equations start to become a lot of times really fuzzy. So be aware of that. Okay, so this part, formulate triplet, then the loss function, that's about it. So I think we are ready to do the static assignment. So the template should be accessible for you. So let's try to do this then. So I already written the same code from the last time. The only differences here are two loss functions. So the loss function proxy NCA, static proxy NCA and dynamic proxy NCA. So let's start with the static proxy NCA. And let's start by defining that embedding matrix, which definitely could be written also as that torsion and embedding. I just don't know exactly will that help or not, and I don't want to experiment too much. I already have in mind many experiments, and I don't want to have problems right now. So let's see, let's try to write this equation. So not equation, but let's start by defining the proxies themselves. So it will not call them P, because P would make us confusing with P will make the confusion with the positive pair. Let's call them just proxies. Okay, let's write them. Just wanted to make sure that I do not experiment too much by looking at some of the notes that I made. I will definitely improvise with this a little bit, because just before session I think I found a couple of bugs, but I definitely think this will work. So at least the static one will definitely work. So self proxies torch and n parameter, the same way as we've written I think in some other models already. So then define the size of that parameter. There are different ways how to do that. One way is just to define it as a float tensor here. And here this will be then, what will be the labels? So len labels of, we are looking only at the training set. So we're not looking at test set at all. So the test set, again, just to remind you, the test set includes different classes than training set. So this is zero-shot learning. So there is no overlap between the, the training classes and test classes are disjoint. So that is quite important stuff that would not be possible with the classification models at all. Also with the circumplex models, this would be not great, but with circumplex models, it might work actually in many cases. Z size, it depends, but it takes more time for the labeling. So float tensor, Z size, so this will be good. Then, let's define that the embedding space will be uniformly distributed. Torch NN init uniform self proxies. So originally everything is random. Labels of training, right? So that's good. So then let's start writing the actual equations. So batch size, will we need the batch size or not? Let me see. I think we don't need a batch size. Do we need it? Okay, let me see. I'm not sure. Maybe we will need it or not. Anyway, so then there is one thing which should be added, in my opinion. I think in the paper they did not specifically write it, but in the model at the end we have L2 normalization, right? So I suspect that we need also the L2 normalization for proxies. Otherwise, I'm not sure that this will be a great way to work with this, but it might help, it might not help, I'm not sure. Might help. So anyways, even if you don't add it, it should work anyways, but it should work better in my opinion with this. So that's one. Then there is another small issue that indexes for classes right now are not starting from 0, because as you know that we're selecting from extended MNIST dataset some classes, like for example the YIDX right now contains something like 3, like 23, 13, 3, and so on. So class indexes, because they are selected from the full dataset, not from this kind of relative data set just from the training set. So and what we want actually is something like this. So I want my relative labels to be if there are like the 3, one is maybe the the first one, then this will be the second one. I mean the first one, then maybe this will be something fourth, and again this one is first. So I want them to be relative to just to the training data set, not to the full data set. And so far it was not matter. So because so far we just checked if the class index match or don't match. In this case we actually don't select that only the class indexes match. We also need to select from the embedding matrix consequentially each embedding for each class, and then I cannot just use like some numbers like these. I could probably make very large embedding matrix and just ignore some of the rows there, which maybe are a better idea. Just realized. Or maybe I can show you how to do this with relative indexes. With relative indexes it will be confusing in my opinion. Okay, let's not do the relative indexes. Relative index, but except if I will not do the relative indexes, I think it will just make it difficult for the negative sampling. Okay, let's do the relative indexes. So the relative indexes can be achieved following way. So You could also make your own data sets, like that already gives indexes not from some random integers from the whole data set, but just from 0 till maximum labels of train. But now let's do this manually here, because otherwise it will take too much time. So, okay. So these relative will be 4. Let's see, so y index, y each, let's say yi in y index, let's yj maybe, so that there's no mistake between yi and y index. So y relatives will be, append will be the, okay, let's call it yj relative, just to be able to debug it a little bit if necessary. So I already added some variable called y to relative to train, and here I want to select where yj equals this thing, and then it will produce the true and false, this true and false vector, right, where they match or they don't match in in that class labels, right? So by the way, what I'm right now writing, this is not related to yet the proxy NCA loss, is just fixing the indexes so that they start from 0, not from some large numbers. So, and here the non-zero function, non-zero will select the indexes which, or just basically it should be just one index, which is in that relative set of classes correct one. So if this is like the first one, second one, or third one in that select, so what is actually inside this vector is something like, like 32, 5, 7, 2. So if I have 4 classes in the training data set, it will look like this. And afterwards, if my j, if this thing is, let's say, 5, then the y relative j should be, of course, 1. So this is what I'm doing here. I'm trying to map from this kind of classes to just to something which would look like 0, 1, 2, 3. So that, and the data set right now is made that it will select classes from the original class distribution. That's why we need this. So yj relative, and here at the end I think we need item, like that. Hopefully this will be fine. And then finally, just let's convert it back to the long tensor. jrel is torch long tensor jrel. So these will be relative ones. I will add breakpoint here and check if there is no bug so far. Let me see. So it works technically. Yeah, so you see, it's actually a really nice example. So you see that we already have the triplets here. So the 0, 0, 0, 1, 1, 1, 2, 2, 2, 3, 3, 3, 0, 0, 0. And before, if I don't use this, let me see how the original looks like. Dix. So yes, you see 4, 4, 4, 0, 0, 5, 5. And it seems like that it's no big deal, but the problem is that I bet that the maximum value of these will be larger than the other one, max. So there's a 5 maximum value, and from relative, maximum value is 3. So it means that in this kind of case, for my testing on the locally on this computer, which don't have GPU, I have only 3. I think there I have only 3 classes. Let me see for the training. Oh no, I have 4. Yeah, I have 4 classes for the training, but already the original distribution included the 5 here. So you see 0, 3, 4, 5, but it's not 0, 1, 2, 3. So that is what I'm doing here. I really hope that this is clear, because this is really simple stuff. This is just mapping indexes within the dataset, because in the dataset I don't have indexes starting from 0. That's why I'm doing this. Okay, so that is good. So that we did already. So then let's look at the next step. Next step. Da, da, da. So the next step, I think, could be the distance measurement. Not the distance measurement. Yeah, but let's think. So I need the proxies. So I need the proxies. Yeah, so we can measure the distances between the anchor and all of the proxies. That would be good. Anchor with all of the proxies. I can do this definitely. Where are my notes? Okay, found it. Okay, so let's then measure the distances. Okay, distances D. Let's call them D. F. Pairwise distances. Pairwise distances, right? So now we will have the anchor point, which will, so we'll need also probably a loop to go over all of the triplets. So let's write then losses for I in range of 0 and by the way, the static assignment works also without triplets, but let's keep the triplets so that for the dynamic assignment it would be easier to understand. So okay, I think this is fine. So we're going by each triplet, right? Right. Let me then next thing. So YA, so this will be the anchor point from Y relative, the I, so that's good. Then Z anchor will be Z from I, right? Then maybe we should select out Z positives and Z negatives, right? All of the possible combinations. So let's write with the large Z, because this will not be actually just one sample. Z positives, so these which match this guy. These will be then Z I plus 1 till I plus, so there should be 3, I think, like that. So because the first one is anchor, and then I have 2 choices to choose. Okay, so that should be good. Then okay, it actually added me I don't like this syntax. So anyway, so for the negatives, this will be ZI plus 3, and everything else till the end. These will be negatives. So all of the negative Z's, all of the positive Z's. Except there is one more problem, because they might unfortunately repeat. And this is really something that I should address here. Unfortunately, I cannot select them immediately like this. So let's start by selecting indexes first. So Y relatives, so these, sorry, I'm just really confusing now you. But anyway, so let's try to do this as I did before. And sorry, so Y not used. So basically Y was not used, but Y not A. So all of the y's which are not anchors, so y relatives, and because there is a possibility that triplet class might repeat, especially in this setting where I have really like few classes on CPU. That's why I need additional step to ensure that I don't include in negatives some positive sample. But if I had like a lot of classes and I'm sure that they will not repeat in this batch, then I could make it easier. But unfortunately, I forgot about that. So I plus 1. So these will be all that are not anchors. So these are all which are not anchors. So then from all which are not anchors, I need to make sure that I select the positives one. So these will be the y. Actually, these are large y because there are a lot of them. So large letters means that there are multiple samples. Small letters usually means that there's just one sample. So y positives will be then all of the not i's where they match the y I. And actually, I don't like that this is y. Maybe I should directly write them as z's. So let's write them z's not I. And these will be z's. And then select directly z's here. And these will be z's, p's. So these are all positive pairs, possible combinations. And these will be all negative possible combinations. Right, so this is good. Right. Yeah, okay. So that is fine. I'm just thinking more a little bit. Why do I do this? Just a second, because I think maybe I should not have done this at all, but let me think. I need the negatives, positives, but this is, so from the proxies, I will select the index, which is known already. I already know the index. I think for the dynamic assignment, I need also to do some sample mining. So let me think. So ZA. This is my target class. Sample triplet. Formulate triplet. So I have the triplet. I could sample the closest and hardest way distance. I guess it matters much more for the dynamic assignment. I don't see why I would need to do this now for this. Z distance for negatives. Negatives, I include everything. Maybe we can save this code for the dynamic assignment. If you've written already this code, then please save it to the somewhere like copy out for the negative assignment, because I'm suspect that we actually don't need this now, except maybe just to Okay, let's keep working with this. I think, okay, yeah, no, let's use it also for the static assignment. So anyways, sorry for confusion. So, okay, for the static assignment, there is the sample mining procedure, which we are at the step of sample the triplet. So the positive distances, so this will be again very similar to what we already did. F pairwise distances. What we're going to do here is we will swap probably here at this moment the anchor to some which is not as good as the anchor itself, maybe. So well, here let's say then ZA expand with the same like that shape as GPs. Okay, I don't like this. I confused myself, I think, because I was focusing on the dynamic assignment as well. So, okay, let's not use this. Just leave it as so far. So I will copy this part of the code. Please do not delete it. Just copy it somewhere. So let's make it simpler. Otherwise, it will be super confusing. So, okay. So we have the Z's. Let's select directly the proxies now. So we have the Z's, we have the relative Y's, so we can select actually the proxy. So the proxy, prox P, the proxy positive one will be the proxies selected by the YI. Yep, so this one. And then the all negative proxies, or actually in that equation, they use the large Z, which most likely means that just including all other combinations, which then means that just all other proxies there. So that is that part. So we have that proxy P. We could do then sample mining with regards to that proxy P then. Okay, let's do that. So with regards to the proxy P, and here we can actually use the same code. So proxy P is here, then we can take that code that I just wrote again with Y not A, and here we then use the Z except Y not A. I don't like that it's not including the AI itself, so let's say Y positives, all positives, and here starting from the I itself, because now we are replacing the ZA actually with the proxy. You're replacing the ZA with the proxy. Actually, ZA, maybe it's also not good to add it here. So Y positive replaced from proxy, right? Y positive, Y relative. So this is fine. Proxy is good. Good, good. So we are selecting, we're expanding this to that. So that's good. And then we need also just the all Z positives. So this will be YP, and ZPs are just YPs, where they select the YIs. Okay, so and then we calculate this. So again, sample mining is not all mandatory. I think I'm actually sure that it will work also without the sample mining here, but I think it should help. So DP, it should do better results basically. Proxies, P, fine. Distances between all of the positive ones. Right. And then we want to select the maximum distance from these guys. Okay, so that's about it that we need to do. So this will be then J positive distance of torch argmax. So we want to select the worst distance from the proxies from the same class, and this will become the kind of our anchor point, the main from which we will work forward. Okay, so I think this is fine. Argmax dp. So then let's write the upper part of the equation. So this will be then the final dp. But how we could write it then? I already used the parameter dp, but how could I write it? Unfortunately, use that one. Okay, let's call these guys dp all, and then call this dp. dp is dp all from jp, so, or just j, so this will be the index that I want to use, or jp, because maybe I will use another index as well. So jp. Okay, so what I did so far is that I have a triplets. I'm selected, but I'm right now not sure that I have only triplets. Maybe there's more combinations of more same class samples in the batch. So I selected all of the same class samples here based on this first anchor here. Then I selected, then I calculated the distances based on predefined position in the proxies here, which is, this line is static assignment basically. Oops, this line is static assignment. So for the proxy, so I'm selecting some proxy which is defined in that table myself. So, and then I calculate all of the distances here, except I forgot to add p. So this is a Euclidean, not the L2 distance. And then I'm selecting the worst sample. So selecting worst sample. So this is a hard mining. Okay, nice, I see question. So why are we expanding proxy P? Yes, you're right, there is a bug. Thank you, Mattis. Mattis helped me out. So this is a bug here. It should be expanded to the same shape. So the expand means just copy the pointers to the same tensors so that they would match the other shape. It would not work always. It would work only if the if the last dimension match or the first dimension match. So if there is no match between dimensions, that function would not work at all. So great, Mattis, thank you very much for this. You helped me. So cookie, thank you, Mattis. I think last time also Mattis helped me. So we're selecting the hard sample, then we are selecting the positive sample here, which is good. So dp is good here, so that is good. And then the negative samples means that we need to select from the jp, which is so zp, zp. So I selected that guy. Then I need to select from JP. So these will be ZPs. From the all other proxies, I need to calculate the distances. And this might be a little bit pain. Or not. Okay, I think it will not be that painful. So Okay, let's do that. So the ZA, the real anchor which we're going to use now, this is at the ZPJP. So I selected the anchor based on hard mining here. So the ZA now is at new location. And will use that anchor for the negative proxies. So the one thing I could do is to exclude the positive proxy from the negative ones. But in the equation, I don't see specifically that they do this. If we will do this, I think it should help, but I don't see that in the equation at all. So let's say dn. By the way, let's call it dn all because it's not include the dn the correct proxy is not excluded here. So ZA will be expanded to the size of proxies. By the way, again, I'm calling this dn all because I did not exclude the proxy yi, but I could exclude it, and I think it might help. So not excluded yet the proxies ja. So kind of the loss function might work not as efficient, but maybe it will work so efficient. So I'm not sure, like in the formulation in the equation, it seems that it's not excluded. So pairwise distance between ZA, which is now selected from this sample mining, to all other negative samples, which seems okay. Proxies, yeah. So we are actually measuring the distance between the proxies themselves. That's good. So okay, now we will add writing the loss equation. So loss is torch mean minus torch logarithm, and then the inner parts. So torch. By the way, I will do the soft division there, so that there will not division by 0 would not happen, and maybe I think it's not. Would it be possible to be also a logarithm of 0? Maybe I should add also there something. Okay, maybe let's add some couple of epsilons to just to make sure that nothing bad happens. So torch exponent of minus. Okay, yeah, again I did the wrong. Yeah, thank you. Now the gins help me. I don't know why I'm doing this. So gins, thank you. So then the D positives minus right. So this will be plus epsilon E minus 8, so that this division would work always without any problems. Torch, and up and the bottom part, there is a summation as well. So torch sum of the torch exponents of the minus DNL, and let's add epsilon there as well. 1e minus 8. So this is, I think, called soft division or something like that, where you ensure that this will work always. It will not be division by 0. And then at the end, need to think a little bit here. So if there would be the distance of 0, then that would be 1. So there should be fine of that. It's maybe even not possible to get the division by 0 except if it's like rounded somehow. Let me double check. Maybe I don't need such complex equations. So exponential. So let me see. Can I get it somehow? Only if this would be really large number, then it can be rounded down. But it cannot be really large number because we have L2 space, which means that it's not possible to get this equation to blow up, at least as far as I understand. Maybe I'm mistaken, but I think we don't need the epsilons there. So, because the L2 space prohibits the distances to be super large to blow up the equation, so I think it should be fine just like that. Yeah, hopefully I'm not wrong. So that part, so we have the loss here, then we add losses, append loss, and then at the end the final loss should be torch mean of losses, except maybe we should stack them also, torch stack losses. So let me check if there's no bugs, and then I will drop some of these lines to the Jamboard. Okay, there is a bug here. What the crap? So let's add here a breakpoint. How this could happen? I don't expect bug in that line. So proxy is P. So this is the selected proxy of 32 dimensions, and my ZPs are something completely wrong here. Oh, sorry, there's a bug here. It should be from Z's, selected from Z's, and I selected from Y's there, from Z's. Okay, now it should work. So, of course, I cannot select Z's from Y's. So, hopefully now, oh man, there's another bug there. What is not liking it? Okay, I need to select Z's also. Oh. YPs, Y relatives, or these are not actually positives, so these will be just all Y all, Z all equals Z from I ahead, Z all, ZPs, now they are correct, hopefully. At least there is no crash right now. Okay, I had some few bugs there, so regarding the selecting Z's, but in general the equations are not so long. So I will now drop some of these lines to the Jamboard. I will annotate also some of the lines which I changed right now. So I changed these few lines where I select ZP. Other lines I left the same as before. So let me see. So I'm dropping this to slide number 5. This bottom part of the code, the upper part of the code was already, so let me also drop the upper part of the code, just in case somebody didn't catch it. So that will be also to the slide number 5. And now I'm gonna upload this stuff to the servers and test out if it works properly. What was my run path, or what was the run path? experiment. You could also run this on Google Colab if you want. Really hope that this is gonna work for the first time. Because like one of the bugs that I made while I was preparing this workshop was that you also can like flip around. So in the equation, you could calculate the proxies. So I mean, like anchor as proxy, and then the positive pair with the hardest positive and negative with regards to the proxy, not the anchor with all proxies, but that the anchor itself is proxy. You could do that as well. You flip it around. It should work as well. So, but yeah, it seems, the result seems encouraging, really nice. I will drop those also to the Jamboard just now, at least from the accuracies which I get from the console. We will see how it looks like in the embedding space as well, just in a second. So this is the Jamboard. Where are my code? No, in the code, but the results. So the results after just the third iteration, I have 92% accuracy after the third iteration. It seems to be working really nicely. So I will drop this to the Jamboard. Slide number 6. So this is epoch third. Already we can see nice clustering happening here. And the accuracy is growing and the loss is dropping. Except the test accuracy also is dropping, which is not cool, but we'll see what happens. Hopefully it will start to improve. So I have now already the fourth epoch. So we'll share how the fourth epoch looks like. I see actually some clustering also in the test space. There is something happening here. We'll see what happens when we train it more. By the way, the initial accuracies are also quite nice, because I already have accuracies after epoch 6. Even for the test set, I have 73%, which maybe in the plot it do not look like really cool result, but in the accuracies metrics it's actually not bad. So after the 6th epoch I already have 73%, even though the loss curve do not look like amazing, you know, impressive. So yeah, so the test accuracies for the zero shot setting are not really increasing that much. Maybe it's also a hyperparameters issue, not sure. So it stays about 79% and so on. Okay, while I'm training this model, let me ask in the chat, so is it working for you? So plus, minus. If something is not working, let me know, and then we will do the dynamic assignment and talk about how to implement it actually. So I will open the next task as well in the Jamboard, in the classroom 4.3. Okay, so I'm open the task. So you already see how to implement interesting stuff directly from the papers. I'm thinking maybe for the homework I could give also some paper to implement, you know, or maybe I could add some. Oh, nice, really good. So we have two first prize winners, the Matis and Gins. Both are really good students as far as I know. So I remember Gins was good at previous course and Matis has also been good so far with the collaboration that we had. So, okay, let's then talk regarding the next steps. So, while it's maybe I will later share the results when it finished the training. So, but the dynamic assignment, that is even more interesting stuff. So. And it's actually a little bit challenging because you would think that this means that you don't need to know any classes at all, but it actually do not work that well without knowing any classes at all. So here, let's see. Oh, Kristaps has also managed to finish, so that's really nice. So here the idea is following. I will try to like also annotate it a little bit. Okay, maybe I should start working out by some other way. So, okay, actually we'll try to copy. Can I copy this stuff that I did here? Let me see, can I do this? Control, Shift. Okay, it does not work. I cannot copy stuff in the Jamboard, unfortunately. So then I need to draw it again. So I have again the proxies matrix, right? So proxies. And again I have the same task where I want to select different proxies for different classes. But there is the problem that in this case, I don't want to predefine which row belongs to each class. So I want model to discover itself which row belongs to each class. By the way, I think there's again a lot of room for improvement, like research. If somebody is interested in especially this problem, I can give you some hints later and you could do some research on this stuff because I don't think it's solved yet, but you could, yeah, you're right. I could do the screenshot. That might be, but I already draw it. So sorry. Yeah, so I already draw it, unfortunately. Okay, so I could do the screenshot, but I also will use this picture to illustrate it a little bit more. Just this one. Let's see. So okay, so I have this picture where it is, right? So yeah, so the dynamic assignment. So the dynamic assignment tells this that we don't need to know how many proxies do we want to use. By the way, they are very tricky in the paper about this stuff because they want to tell some a little bit different story. So the promise for this method would be that I don't need actually to know the labels, right? So that I could work without labels. That would be perfect. So like in an unsupervised manner. But it doesn't work at all that well for unsupervised manner. So that's why in the paper they are very picky and tricky. So they say that a dynamic assignment helps to reduce the memory footprint, which is a little bit funny because I don't think that the proxies matrix kind of is problem for memory. So, but imagine in this case if we are reducing. So if we originally had, let's originally had 1, 2, 3, 4, 5 classes. This we have 5 classes, so let's write originally we have 5 classes, for example, and this would be the static assignment. So let's, maybe we could, yeah, so this would be then the static assignment, static. And I think there is an opportunity to make this method also without the labels. So that is what I mean by the the opportunity to do the research. So I really think that there is an opportunity to do very, very good research on this field. So what I mean by that is that here in that paper they say that with dynamic assignment you can define that let's not use 5 classes, but let's use 3 classes, or use more classes, by the way, as well. You can do that as well. So, but let's use just 3 classes. Originally we have 3 classes in the dataset, but we will use only 3 proxies. Okay, now we have serious problems, because then how we will select like the real proxy which we're going to use here and here if we don't have the same number of classes and proxies. So, and then they have in the paper some solution for that, which definitely can be improved. I guarantee you that. So is that so the solution that they use is this one. So 5, I think this thing, right? You know, proxy approximation error by the worst approximation among all data points. Where do they use this stuff? Let me see. Not sure why do they need this thing. And we will show the concrete loss gets tighter, smaller approximation, blah, blah, blah. Okay, that's not important. So anyway, so what is important is the dynamic assignment, which is done by non-differentiable method, but at the same time we can just select that embedding and then differentiate it. So like use it as a constant. So here again there is the room for improvement. Let me write down. So room for research. So basically this is non-differentiable, but you could definitely even if you want later I can consult, but basically you could make this equation much smarter. So anyways, and you would select the kind of your proxy based just on the minimal distance between the sample that you're looking here, or maybe some other sample. Let me see. What about the proxies for the other guys? Yeah, if you look here from this sample, you would snap to this proxy. If you look from this sample, you would snap to this proxy. So if there is the yellow one somewhere right here, and this guy is closer to this guy, then it would snap there. Maybe I should even draw this. By the way, right now the colors doesn't match the scheme, so let me fix the colors. So this will be the green, right? So we have red, green, and let's add yellow. So let's add yellow triangle, right? So let's have the yellow triangle here, and let's place it somewhere here. So, and what actually would happen now is that some of these guys would snap to other proxy, right? So these would snap together and these would snap together, most likely. Maybe even this would snap here. So these all would be identified at that yellow proxy, not as something which is predefined before. So let me ask in the chat, is this clear so far? Plus, minus? So if something is not clear, let me know. Again, what I'm saying, we have learnable proxies, learnable matrix, where I want to snap the, what I mean by snap is just to find the distance, which is the closest to some arbitrary proxy here, which is not based on the dynamic assignment, I mean the static assignment. So here we dynamically just select some proxy based on their distance, not based on predefined indexes. So I see 2 pluses in the chat. That's good. Hopefully Matthias is also there. So anyways, I don't want to take too much time of yours as well, of course. So let's keep trying to finish this as soon as possible. So let me also show some other examples here. So here they say that using this method, what they can achieve is a really fascinating result. So first of all, they can achieve even higher accuracy if they add more proxies per class. So that is one very interesting conclusion here. So even higher accuracy if I add more proxies per class. So there's like the index, how many proxies I want to add. So I multiply the original number of classes by that index. So if I have twice as many classes, twice as many proxies as the classes, I get a slightly better accuracy even. So that's one interesting property, right? The other very interesting property is this one. So if they compare to other methods, at least they claim this again, especially for zero shot setting. Let me check, did I describe somewhere that this is a zero shot? It doesn't seem to be so specifically. Which only enables us to surpass state of desertion, but okay, so they do refer that they use zero shot, but I don't think that they explain in very detail of the disjoint of classes how they do this. But anyway, here they compare it to the triplet loss, for example. Again, I mean the accuracy for the top one. So and you see that. So what is actually struct loss is a little bit higher here. So they say that even if they select only 75% of classes, so originally if there were like, if there were 10 classes and they just select, I don't know, like 7 or 8 classes, they will still get higher accuracy than triplet loss or any others. So that's really fun. I think even with half amount of classes, that they would still surpass them. So we could try to write this. Let's try to do this now. At least from my experiments, it does not work that well. There is definitely some kind of secret sauce, or at least that basically there definitely must be improvement in that dynamic assignment. Maybe they just left it out because they have some proprietary research. You know, like they don't want to publish something that works better. So, but you can publish it if you want. So anyway, here, then there is the static proxies. So let's take all of the code from static to move this to the dynamic. Where's dynamic guy? Here's the dynamic. So dynamic ones, and then I also will change dynamic here in the loss function which I use. I use dynamic loss function now. What is this? Okay, it seems hopefully good. So, okay, so then let's add some other thing here. So integer multiplied by the ratio, class ratio. So I already defined one parameter, which is the class ratio, which is 1.5, which is more than originally. So that is what I added already, except just a second. Appearance, toolbar. No, please show me toolbar. Yes, back. Okay, Z ratio. So labels, Z ratio, this is good. So we have that part ready. Then here, again, the only small change here, actually I will drop this to the Jamboard. There's not many changes actually here in this part of the code. So then the assignment will be different, as you know. So So now I will drop this in the slide number 9. And now let's look at the assignment part. So the proxies, positives, so where they match. So selecting proxy P positive, static assignment, we need to change it to the dynamic assignment. So the YI, ZPs. So unfortunately I need to use then here, not unfortunately, but I will use here then this ZA, which will be overridden later. So this first ZA, which will be just from ZI. And now I need to select which will be actually the proxy P, so this assignment. So the proxy P assignment now should be done by using... Oh, seriously, I did a bug there? Yes, you're right, thank you. I don't know what is this stuff about. Yes, thank you. That is so good that you're following what I'm doing. So class ratio, integers, you're like my super intelligence debuggers, basically all of them at once, like at least 2 people who are really smart and debugging me in real time, so that is really cool. So anyway, I'm now updating that to the slide number 9, and thank you, Matis, for the second time you saved me today. Where is that cookie? Okay, Matis. Thank you. So this is true. So I wrote that equation a little bit wrong here. Okay, so that is good. So now we have ZA, we want to select proxy P, that is our task. And to select proxy P, we will use again the distances. So this will be the distances of candidates, basically. Distances of candidates of proxies. Or maybe let's call them just proxies. Distances proxies. From the ZAs. So I want to expand ZAs to the proxies. Not ZAs, but ZA to the proxies. So I have these proxies selected here. There's a bracket missing, seriously. Yes, thank you. Whoa, I probably did not sleep too well if I'm doing so many. No, but there is no bracket missing. How it's possible? No, there is no bracket missing. It was correct. Now you were a little bit off, but okay. But thanks for following anyways. So it might as well be missing, but it's not missing, at least as I see it here. So anyway, then D proxies. So from the D proxies, we will select the assignment. So this will be the assignment. YA, where do I use more YA? I do not use them at all, then later. Okay, so this will be then the, let's say, how we can call this then. Let's call it Y proxy. Y prox, this will be then the torch argmin, so the closest proxy here from the D prox distances. And now we will use this guy as the assignment here. I will use this guy as an assignment. So basically these few lines should be dynamic assignment. And of course there is a lot room to improvement to basically do this better. Okay, so I added this as a dynamic assignment. I upload this to the server. We'll try to render it again. Not render, but run the experiment. You'll see if I don't have any bugs there. Seems to be working so far. And I think now you should be smart enough to see how to implement stuff from the papers. Maybe my idea maybe is to, so I will select one more paper. That's all, again, different method for the deep metric learning, basically also something based on triplet loss, and or something like this with the proxies. And that could be your homework. I will try to make sure that it's not too difficult. I will just maybe give you as a homework just a paper to implement. So the goal here is that the people who finish this course very successfully are capable of writing new research and publishing it in journals, right? So this will not be like just for the publishing. So I mean, not ready for publishing, but at least something in that direction, you know, like if you can implement papers for yourself, that would be really good. So I think that could be a homework. Right now, the proxy assignment do not work super great. Or another homework could be just to improve this, but okay, it's learning something, but it's not giving like super great results. But anyways, I will drop this code. I will drop this code to the Jamboard. And maybe I can give you some hints how to improve this convergence. There's definitely something like omitted from this publication. That is also quite typical, unfortunately, with some of the Google research. Yeah, I did change the loss function. You're right, against C, dynamic proxy NCA. That is something that should be changed as well. Yeah, maybe I should drop it in the Jamboard so people would understand that we need to be changed. Yes, that is true as well. But there are some behaviors of the way how the equation works and the embedding space, how it looks like, that I'm not totally sure that everything that's necessary are given in the paper. And I also think, if I remember correctly, that original implementation was not published for this paper. So I think there's only like secondary implementations. So it's not that easy to verify how to repeat those results. But at least static assignment works good. So we'll see. Okay, so this vanilla version in the epoch 8 do not show super good results. But the loss function is converging slowly, I mean, like reducing the loss. So it will think what we could do to improve. One option is to exclude the other proxies, maybe, but at the same time, I don't think it might help, but it will not change the behavior drastically. So then hard mining here, maybe we could include just all positive samples, not just the hardest sample. So you shouldn't, I mean, like if you want, you don't need to play around with these things now. You just like, we'll try to quickly give some hints how to improve this. So DP all selected from this guy. Might as well just not select the hardest sample, but select all the samples. So the torch mean of DPs. So select all samples. Then here, with regards to the other guys, JPs, DPs, I would actually select the average from all of those ZPs and use that as also as my anchor. So that's another. So all of these things are not included in the paper as far as I know, but we could be used to improve the situation. So ZP mean of the dimension 0. So I want to have not the hard sample, but just the average of those all. So maybe that could help a little bit. So this will be a hack 1. Averages, not hard sampling. So that one. The other one maybe could help that initially it's not uniform, but maybe all in the same point, collapse on zeros, initialize as zeros. By the way, if these hacks will help, which I'm not sure that they will help, is then I will also share them on Jamboard. So 14. At least they are really like kind of floating around in that space and not really giving me good results so far. So we'll kill the process, run it again. Okay, we'll let you catch up. Run it again. Let me show you. So here I added these guys, and here I added the 0 initialization. Well, let me run it for a few minutes, and then I will give you some results. So I'm back. Let me see. What do I have here? So with these few hacks, I see a little bit of improvement, but of course the way how this whole stuff works, it's not super great anyway. So, but I can see some improvement now already. So what I did, I will also annotate that a little bit quickly on the Jamboard. So, so this is epoch 5. Hopefully with a lot more epochs it will be better. At least on the test space you can see that it is a little bit of clustering stuff happening. So, and the accuracy is increasing, the test accuracy at least. What I did is just to add the quiet. Thank you. So proxies init as zeros, and then the other hack that I added is that not disabled hard sample mining, basically around what I did. Let me add those lines, because it's already so unstable. So I think the kind of the sample mining do not help here. So disabled hard mining. And then it works a little bit better, but it's, as you see, it's not super great. So yeah, so that's about it for today. I mean, the static assignment works well. The dynamic assignment works not as good. There is definitely room for research, as again I say. For example, for that part of assignment, it could be improved. The other thing you can do is also, I'm not totally convinced about the argument that the NCA loss, which is used here, is the best one to use here. You could use also some other loss, like for example triplet loss or contrastive loss here, that could also yield really interesting results. So that is also another thing that could be added here, and yeah, and then we can do the homework. So I remembered one more thing. I forgot to mention that here you have one extra option. So let me rewrite it. So this will be 3, 4. So 2. So we can also do the KL plus softmax. And in that case, you could have not probabilities which are not just 0, probabilities like 0, 0.5, 1, but in the categorical cross entropy you only have probabilities for the ground truth only 0 or 1. So there is another way how to do classification, but the probabilistic way for uncertainty there, that still kind of do not represents the similarity between classes. It just makes to like smoother transition between classes. So and the KL type of like the KL divergence for basically KL divergence for the classification task is also not great actually. So yeah, so that's it for today. I think hopefully this was really interesting, and next time we're going to start working with GANs, so generative adversarial networks. So hopefully that will be also fun. So that's it for today. Bye bye.